Hi, so in this video we're going to apply what we've learned about first order differential equation with constant coefficient and constant term to the problem of dynamics of market price. Okay, look, what you can see over here is a market model that we've exploited extensively and intensively in Introduction to Economic Analysis. Look, the only difference is that before we were using A, B, C, D. Now, because we are using A and B in context of differential equations, so I just replaced them with alpha, beta, gamma, and delta. Okay, and look, we can solve this model quite easily using Cramer chain. We're going to start with the static version that we were doing last semester. Okay, so equilibrium condition here was that QD equals to QS. So they are equal to the same value, right? So we get that this equation, this system of two simultaneous equations can be transformed into this, right? Then we were rewriting it into matrix notation, right? Of course, those two I need to take to the other hand side of the equation, and I'm going to have 1 beta negative delta Q P equals to alpha and negative delta. Okay, we always start by calculating the determinant, and the determinant here is negative delta minus beta, or preferably for us, negative beta plus delta. Then, by Cramer's rule, we can find Q and P. For us, P is important, but let's solve for both. So first we calculate AQ, which is equal. So I take the vector of constant terms, I replace them over here, so I get alpha, gamma, beta, minus delta, and out of this, I'm getting that this is alpha, negative alpha delta, minus beta gamma. Yeah, okay, then we find, of course, we should notice right away that because both of these are positive, we've got minus in front, we know that this is different than 0, so we know that the equilibrium solutions exist. But we've done this model so many times that we probably remember. Okay, then we look for AP. And so now I replaced this column, and I get that this is 1 alpha negative gamma. So I get that this is negative gamma minus alpha, or simply negative alpha plus gamma. Okay, so what are the equilibrium solutions? Well, equilibrium price is given by negative alpha plus gamma over negative beta plus delta, which we clearly see we can get rid of the minuses, and this is the outcome that we are used to. We clearly also see that the price is positive here. And then we get to equilibrium quantity. And equilibrium quantity, again, we can take minus out. So those two minuses and this minus will cancel each other out, and we're going to get them alpha delta plus beta gamma. I'm sorry, I forgot the minus over here. That's what this that was missing. So of course here we will have minus beta delta over beta plus beta gamma over plus delta. Okay, so those are the two solutions, right? We can also put those equilibrium solutions on a graph the way we always did. And remember, just we put Q over here, P over here, and first we've got demand. And demand, of course, starts at alpha. It goes down until, look, if I substitute Q0, I'm going to get that P is equal to alpha over beta. And then for the second one, we start with negative delta. And here we have supply. And by the same token, we're going to have, if Q is 0, then we will have negative, we will have gamma over delta, right? And of course here is equilibrium price, and here is equilibrium quantity. Look, before we were also using comparative static derivative to see, for example, what happens if demand is increasing. How could we see increasing demand over here? Look, increasing demand would be bigger volume of alpha. Let's just call it some alpha 1. This is alpha 0. Still have price over here. And look, once demand is moving, look what is happening. The new equilibrium price is no longer here. It's over here. And this will be equilibrium quantity, but again, this is not that important to us. Look, but what is then happening? We were assuming previously that this all happens in one single moment. Like alpha 1 goes up, and we go to another equilibrium. But this is not the case for us right now, because now we can introduce dynamics into the model. Look, what happens now is, if the previous price and previous quantity we denote with Q of 0 and P of 0, we can take them both as our point of reference. And look, now we want to analyze what is going to happen when this demand shifted, for example, and it's over here, but the price did not catch up. So what is going to happen then? Is the price going to get to a new equilibrium or not? Well, for this, we need to introduce into the model a little bit more. But we need to introduce dynamics. For example, we can introduce a rule that will tell us what is happening to the price depending on what is the relationship between quantity demanded and quantity supplied. And we're going to do it like this. Look, we introduced derivative dp dt, and look, this derivative is telling us how price is changing. And look, how price is changing depends on what is the quantity, on what is quantity demanded and quantity supplied. Okay, and look, so I can express it as a function of excess demand. Look, here, this J will denote for us adjustment coefficient. Now, what is quantity demanded minus quantity supply? Of course, this is excess demand. And let's figure out how does it work. Look, if demand is bigger than supply, what is the rational thing to do for the companies? Well, you can imagine it like there is a big line of customers in front of your store, right? And you know that they want to buy the goods you sell. Probably you don't even have enough at the moment to sell them. What is the rational thing to do? Increase the price. As a result, some of them will decide they no longer want to buy it. They no longer want to buy it. Well, but still you can make more money on it. Okay, so look, we see that if quantity demanded is bigger than quantity supply, the price on the market should be rising. But of course, this means that the derivative dp dt must be positive, right? Now, let's reverse the situation. What if quantity demanded is lower than quantity supply? Now, like, the situation is reversing. So, your company produced so much that they cannot sell. You do not have enough customers. So, what is the rational thing to do? Well, decrease the price and attract more customers. So look, if quantity supplied is bigger than quantity demanded, the price would be falling, or derivative of price with respect to time would be lower than 0. Okay, now, if in order to introduce this dynamics into our model, we need to make a certain assumption on J. And this assumption is very easy. Look, it's just J needs to be bigger than 0. Because look, if quantity demanded is bigger than quantity supply, price is the derivative of price is positive, which means price is rising. If quantity supply is bigger than quantity demanded, price should be falling, so the derivative should be negative. Well, as you see, this condition is met here very well. Okay, so knowing this, we can start solving this one. But look, we're going to do it a little bit differently. We're not going to use Cramer's rule, but we're going to use first order differential equation. Because, look, we can easily substitute this over here and this over here. Okay, so we've got that dp dt is equal to j times, instead of qd, I'm writing alpha minus beta p, and then minus qs, so now plus gamma minus delta p. Okay, now I can organize everything and multiply by j. And look, I'm getting that this is the dp dt is equal to minus j beta plus delta p, right? This collected with this times j, and then I've got plus j times alpha plus gamma, right? Okay, now let me just put this on the other hand side of the equation. And look, what do we have over here? Look, I hope you can see the resemblance to the differential equation that we've used before. Because look, this is our dy dt, this whole thing is our A, P is our Y, and this is B. So look, with this knowledge, we can easily find the solution to this differential equation, because we can express now P as a function of time, so we will have the time path of price, and it must be equal to P0 minus B over A times e to the power negative AT plus B over A. Okay, let's see how much is it. Okay, we've got that this P0 gonna stay as P0. As you can probably guess, this is our P0. Our price, for example, before demand shifted, of course it goes the same way for supply. And now, look, here we have B over A. B over A is J alpha plus gamma over J beta plus delta. And look, right away we can notice that J's can cancel each other out, and we get an expression like this. Where have we seen this expression previously? Well, this is exactly the equilibrium price we've calculated in a static model, right? Over here. So, clearly, we are getting exactly the same result as we got with the Cramer's rule. Probably even in a simpler way. Okay, now this must be multiplied by e to the power negative AT plus, again, the same expression, alpha plus gamma over beta plus delta. This, in turn, is equal to P0 minus P in equilibrium times e to the power negative AT plus equilibrium price. Okay, look, this solution already is giving us, but of course, what is our A? I'm sorry, I skipped on it. Now, our A is, of course, J. Our A is J, but with the minus up front, times beta plus delta, times T plus equilibrium price. Okay, and look, what are we getting out of this equation? Well, we get quite a lot. First, we know what is the equilibrium price. And look, in our context, this over here is the equilibrium price. Now, we know from what we got over here that price is different, and the price at the moment of our analysis, so P0, is different than equilibrium price, right? So what do we have over here? Look, this expression that you see over here is deviation from equilibrium. In other words, in other words, we see the difference between actual price an equilibrium price, right? So this is the same deviation that you can see over here. And now the question is, what's going to happen? Look, if this deviation is going to somehow disappear over time, if it's going to disappear over time, it means that actual price is going to move towards new equilibrium point, right? Or maybe it's just going to stay exactly at the same level, or maybe this deviation is going to get bigger and bigger and bigger and bigger. How can we know that? Well, look, the key to it is in the expression that you see over here. Because look, this is the only expression that actually contains t, so time. So this is the dynamic part. It actually can show us whether the price is going to get further away from equilibrium, closer to equilibrium, or maybe it's just gonna stay at the same level. Okay, so let's remind ourselves a little bit about this expression we see over here. Look, I know that it's written here in a very, let's just say, long form, but look, if I would just written it like this, I would written it like as e to the power kt, like y is equal to e to the power kt. Okay, look, this time we've got an exponential function. We were talking a lot about them during our first couple of classes. So now let's use our knowledge. Okay, so let's consider two cases. You know what? Let's add one more thing. You know, over here, let me just add a constant z, right? Now, we are starting at t equal to 0, right? Because we are assuming that we are always starting at 0. So what is the value of this function when t is equal to 0? Well, of course, this turns into 1. So we will always start at z. And look, but in drawing this function, we need to make two distinctions, because there are two possibilities. Look, the first possibility is that k is bigger than 0. Look, if k is bigger than 0, this is a typical example of exponential growth, right? We see that we will start at point z, and then we will be getting higher and higher and higher and higher and higher, right? So we are actually, so this expression is getting bigger and bigger and bigger. Now, the second possibility is that k is lower than 0. Of course, in case that k will be exactly equal to 0, then we can eliminate it from our example, because of course we've assumed away this possibility. But okay, let's just go back to this. We will get back to the model in a few minutes. Okay, now look what is happening now. If k is negative, it means that what? Look, if k is negative, or is the situation in which we divide z by expression a minus kt this time, right? Because k is negative. And look, what is happening? We are dividing z by a bigger and bigger and bigger and bigger number, which means that this entire expression is getting lower and lower and lower and lower and lower. Of course, it never reaches 0 unless we're going to consider the case of a limit. Because look, here we clearly see that as if k is bigger than 0, as t becomes infinite, y is becoming infinite. Over here, we've got opposite situation. Look, if I would calculate limit with t approaching infinity out of z e to the power kt, assuming that k is lower than 0, and look, we are dividing z by a bigger and bigger and bigger and bigger and bigger and bigger number. So the limit is 0. And look, this is how actually we are going to check if the price is going to equilibrium or not. What we need to do is that we need to calculate a limit of complementary function. So of this part. Okay, so how to do it? Okay, look, this is not that complicated. Look, we need to calculate a limit with t approaching infinity out of p of 0 minus equilibrium price. Of course, we could express it as alpha plus gamma over beta plus delta to the power e minus j beta plus delta times t. Okay, and look, what is this expression? This expression is our deviation from equilibrium, right? So this is like our z over here. Now, what is happening is that this is a constant, right? This is initial price minus equilibrium price. This is some constant value. And now we are scaling this value by the expression, by the exponential expression you see over here. And look, now we know that if this expression over here is positive, then this will go to positive or negative infinity depending on the value of the expression over here. But it will go, generally it will become infinitely big in absolute numbers. Now, on the other hand, if this expression is negative, it means that we are dividing a constant by a bigger and bigger and bigger number. So it goes to 0. What is the case for us? Well, look, what have we assumed? We have assumed that beta plus delta, beta is positive, delta is positive, j positive. It has minus up front, which means that this limit is equal. This limit is actually equal to 0, right? Okay, so if this limit is equal to 0, then what is going to be the new price? Look, actually, I hope you can even see it from this, because if we would calculate limit with t approaching infinity out of the entire expression p0 minus p into the power negative j beta plus delta t plus equilibrium price, then how much is this limit? Well, this part is going to 0. So we are just left with equilibrium price. And look, this type of situation where when this limit is equal to some number, not infinity, or not negative infinity, we call dynamic stability of equilibrium. Or or in other words, we can say that equilibrium is dynamically stable, which means that once we get to the equilibrium, we are staying in this equilibrium. Of course, look, because this is a mathematical example in continuous time, well, you might say, oh my God, how long we can wait until this infinity is going to take place. But remember, when we are dividing by e to some power, e, we are dividing by, in this case, we are dividing p over p of 0 minus equilibrium p by e to the power minus j times beta plus delta times t. And look, this expression is characterized by exponential growth. So it grows very, very fast. Well, this stays constant, so actually it disappears very, very fast. And look, we can actually very easily show this result on the graph. Now, look, on the graph, we will see that on this axis, now we're going to grow a time path. This is the graph of a time path. Look, here on this axis we have time, on this axis we have price as a function of time. And look, first what I'm going to put on this graph is particular integral, so equilibrium price. Okay, so now that we've got equilibrium price, we can see that actual price on the market can be above equilibrium price or below equilibrium price, right? So look, in this case, P0 minus P equilibrium is positive. In this case, P0 minus P equilibrium is negative. We are below equilibrium price, we are above equilibrium price. Look, in both cases, what we are going to see here, because this component here is positive and with minus at front, then with time, price is actually getting closer and closer and closer to equilibrium, and of course in infinity it reaches equilibrium price. And the same thing happens from below. The disparity, the deviation from equilibrium price gets lower and lower and lower. So look, of course here we have a case where P0 is smaller than equilibrium price, and above, we have a case where it is bigger than equilibrium price. Okay, so look, now we can go back to discussing what different parts of differential equation actually mean. Look, first, let's concentrate on particular integral. Particular integral that we've got over here, which is equal to alpha plus gamma over beta plus delta, is an equilibrium value. But look, we can mean this equilibrium in two senses. Mathematically speaking, this particular integral represents equilibrium in intertemporal sense. In equilibrium in intertemporal sense, Equilibrium in intertemporal sense means a point into which, if we get, we are staying there. Of course, it might be unstable or stable equilibrium, but this depends on this expression, right? But if we are at this point and nothing happens, we are not moving out of it. But look, this is also an equilibrium in economic sense. And look, those two, as it happens in the example we are discussing, those two are the same. Those two don't need to be. But look, we know that this is equilibrium in economic sense because this is a point at which demand is equal to supply, as economic theory is teaching us. Okay, so now, look, a complementary function, yc, is showing us deviation from this equilibrium. So, and look, it's showing us this deviation from the point 0, so at the start of the analysis, until infinity. Look, this is what you see over here, because we are either above or below equilibrium, and in this case we are seeing that we are getting closer and closer to it. But look, this doesn't need to be the case always. Look, what if we had a situation, what if we would have a situation in which we have, actually we will consider it, but just let's entertain ourselves for a second. Look, let's just say that we have a case where this J times beta plus gamma plus delta is actually a negative number. Look, what will happen then? Then, if we will have equilibrium price over here, then look, this deviation that you see over here would be scaled up by this expression over here. We are assuming, of course, now that this entire thing is positive. And look, with passing time, doesn't matter how close to equilibrium we are starting, we would be moving further and further away from this equilibrium. And of course, if we would be below, we would be going and going closer. And of course, we would reach 0 because the price cannot be lower than 0. But mathematically speaking, the variable, can cross from positive to negative values. Okay, so look, I hope that you now see that. Okay, let's summarize what we've learned. Look, we used market model. We've introduced dynamics into this market model by a very simple rule that price goes up when demand is positive, so when demand is bigger than supply, and it's going down when supply is bigger than demand, which makes perfect sense, right? Now, because of that, we were able to transform the model into a different differential equation. We solved this differential equation. We found that equilibrium price is actually the same as the one we've obtained using the Cramer's rule. But we also established a different fact. Look, in this condition, equilibrium is dynamically stable. Look, we've established that it doesn't matter if price gets above equilibrium value or below equilibrium value, the market forces are bringing this price back to equilibrium. Look, the other word we can use for this situation is convergence. in other words, basically, I'm using this word today, we can clearly see that price converges to equilibrium value and reaches it in infinity. Okay, so look, take it now. Simplifying everything that we said, we can say that actually it turns out that whether we will have stable equilibrium and convergence or unstable equilibrium depends only on one expression, right? On the expression e to the power negative j beta plus delta times t. And look, if this expression is positive, if this expression is positive but with minus in front, then we will have convergence. And look, j is adjustment coefficient. It needs to be positive. It simply says that excess demand causes price to go up, excess supply causes price to go down. But what are beta and what are delta? Look, beta is negative of the slope of demand, right? Because slope of demand in our model, right, QD is equal to alpha minus beta, beta Q, sorry, beta P is negative beta, right? So beta is directly associated with the slope of the demand. And delta, on the other hand, is exactly the slope of supply, right? Because supply function is given by negative gamma plus delta p. Okay, but look, from this we can get a very surprising result that there exist some circumstances in which even if we would have positive supply, positively sloped demand, we could still have market going to equilibrium. Let me illustrate this point to you. Because look, let's assume, look, before we were assuming that alpha, beta, gamma, delta, all positive. Now let's assume that beta is negative. Look, if beta is negative, it means the demand will be positively sloped. Okay, let me just draw you this positively sloped demand. Okay, so we would have price here, we would have quantity here, and demand function, okay, that would, let's just say like this. Like it starts from some alpha, and it goes like that. Now, let's just say that supply is also, supply stays the same, right? So, here we have a supply. Okay, now, look, if beta is positive, negative, and delta is positive, this expression can still be positive, because beta plus delta is going to be positive, is going to be bigger than 0 if delta is bigger than negative beta. Or look, in other words, we could also say that delta is going to be bigger than absolute value of beta, right? So as long as absolute value of beta is smaller than delta, we should have market equilibrium that is dynamically stable. Now, this is the situation, actually the situation described in this condition. So, look, what do we see? Demand is upward sloping, supply is upward sloping, but look, the slope of supply is higher than the slope of demand, which is exactly what we read from this condition. And look, what is happening in here? Now look, if demand is this much and supply is this much, what do we see? Over here, we see that this, if we have, let's do it from the other perspective. Maybe it's going to be easier to understand. Okay, let's start at a point like this. Let's just say that this is the price at some point 1, right? What do we see over here? Supply is bigger than demand, right? Because here we have quantity demanded, which is lower than quantity supply. What should companies do? Well, they should decrease the price. If the price would be decreased to some P2, we will still see that supply is bigger than demand, and market mechanism will still work and bring the price to equilibrium. Does it work over from here? Well, of course, because look, now, if we are below equilibrium, now we see that demand is bigger than supply at this price. What is then rational thing to do? It's to increase the price. And doesn't matter where we start, we're always ending up in equilibrium. So actually, from this, of course, look, this is a hypothetical situation, but it serves to prove a point. So look, it turns out that we would have a case where we would not have dynamic stability on the market if and only if within this simple model, if we would have a case where supply is actually flatter than demand, which is actually even really hard to draw. Okay, I'm gonna draw it like this, but as you see, it's really hard to even make sense of this case on the graph. So we would have to have supply that goes like this, and demand that goes like this, which, as you see, doesn't make much sense. But let's just entertain the idea for a second. Look, here is equilibrium, and look, this is still equilibrium in intertemporal sense. If we are at this point, we are not moving away. But what if the price is going above? Look, now what do we see? Demand is bigger than supply. What is rational thing to do? Increase production. But if we increase the production, it will increase the price. But if we increase the production, if we increase the price, we see that demand is even bigger than supply. So look, we would be going further and further away from equilibrium. And it also works over here. Now look, here supply is bigger than demand, which means that the rational thing to do is to decrease the price. Okay, I know again that I've brought a lot of information in this video. But look, what are the most important things to remember? Look, remember how this market model is constructed, how we've introduced dynamics through the derivative of price with respect to time, which simply tells us that if X's demand is positive, price goes up. If excess demand is negative, price goes down. Remember how to solve this differential equation and what is the condition to a certain dynamic stability of equilibrium. And of course, you are going to practice this with Valeria using different numerical examples in your class. Okay, thank you for your attention. See you in the next video.